Exponential functions are all the rage at the moment with COVID-19 spreading quickly in some countries and not spreading quickly in other countries. So let's use that as some fodder for discussion as we move through this unit. So we've got an exponential function here, f of x equals a to the x, where a is an element of all real positive values, not including 1. Okay, so when we're talking about bases, let's just update your notes on that. So it should be not including 1. So the base can be anything that's a positive number except for 1. The reason for that is f of x equals, if I choose a base of 1 to the x can be any number from the real number system, and 1 to any number is just 1. So that actually can be rewritten as f of x equals 1, which is simply a horizontal line, not an exponential function. So that's why this disclaimer exists here. The shape of the graph depends on that a value, and in terms of COVID-19 spreading, if a was greater than 1, or people who were spreading it were giving it to more than one person, what was happening is we were going to start to get this exponential growth. Okay, and so what the government tried to do is actually take the a value and make it so that it was between 0 and 1. Slowing the spread of it meant that value there of a decreased below 1, and what we successfully happened was a curve that was threatening to grow exponentially then bottomed out again and decayed, or is decaying still, although we have got some sort of slight hiccups at this point here. It's not truly exponential. It can be thought of sort of in that way. All right, so here is what happens when we have an a value greater than 1. We've got growth. So I know by looking at an exponential function, like if my a value is 1.1 to the x, then I know that I've got growth because the a value is larger than 1. And the higher that a value, the faster the growth. All right, if I've got an a value between 0 and 1, for instance, a half, what happens is I get decay. Okay, so this is the scenario that happens. So what we want to do is just experiment around with this base graph f of x equals a to the x and slam in some values. So f of -1 equals a to the -1, and that can be expressed with a positive index as 1 on a. So when x is -1, y is 1 on a, and there's our coordinate point there on both graphs. When x is equal to 0, then y is equal to a to the 0, which is 1. So 0, 1. There it is. There it is. And when x is equal to 1, that's a to the 1, which is equal to a. So 1, a. And again, that point is there, and it's there. What's the maximal domain? Well, x is an element of all real numbers. The domain will be any real number. So you can feed an exponential function any value of x, and it will get you an answer. But what comes out of the function, i.e. the range, is actually going to be 0 to infinity for this particular exponential function for f of x equals a to the x. It's not for all exponential functions, but for this one it is. And that can also be said as y is an element of all real positives. State the equations of any asymptotes. So what's going to happen here as x gets increasingly negative, this line here is going to get closer and closer and closer, but never actually touch it. So it's going to have an asymptote at y equals 0, and it's going to do the same thing over here, y equals 0. So y equals 0 is the asymptote for both versions of those graphs. And when is it strictly increasing? So this is going to strictly increase when a is greater than 1, and it's going to strictly decrease when a is between 0 and 1, not inclusive of those endpoints. So f of x is strictly increasing when a is greater than 1 over the domain all real numbers. F of x is strictly decreasing when a is between 0 and 1 for all reals. Okay, so we've got some transformations going on here, considering the graph of y equals 5x. Okay, so y equals f of x. Okay, and let's sketch f of x first of all. So we've got 5, y equals 5 to the 0, which is 1. So when x is 0, y is 1. So there's our y-intercept. Let's get 2 other points on either side of that. Y equals 5 to the 1 equals 5. When x is 1, y is 5. Out of domain, well, not out of range of the Cartesian plane, but it doesn't matter. And y equals 5 to the negative 1 equals 1/5. So when x is negative 1, y is 1/5. Somewhere down there. Okay, so list the axes, intercepts with coordinates, label the asymptote with their equations. So there's the asymptote along that line there. Make sure you do rule or make indentations along that line there. It's very important that you do show that you know that there's an asymptote there by actually drawing something. Some students don't draw along there and just write y equals 0, to which the examiners will not give you that mark. They want to see you actually do something there. All right, so let's draw my function. I'm hopeless at this with this stylus pen that I've got, so excuse that. Now, problems, way too sharp there, too linear looking there, that bump there. So lots to not like about this, but I just can't do it because I'm not actually writing on the screen. Y-intercept when x is 0, y is 1. What's that? That's the function y equals negative f of x. Okay, so we drop a negative sign in front of that function there to create this function, which hopefully you know when you see that is a reflection in the x-axis. So let's reflect those points in the x-axis. Draw my function. Oh, that's not bad. Okay, this one here, hopefully you know that that's y equals f of negative x. We'd slam negative x into f of x to make that one, and that's a reflection in the y-axis. So that's going to take this one to here, and this one to here. Okay, so obviously again that's not acceptable, but I just can't correct that. So again, forgive me for my sins, girls, but it's supposed to go through the point. Okay. All right, this last one here would be y equals negative f of negative x, which is a reflection in the x and a reflection in the y. Creates a rather nice pattern here. Okay, again, not great there. Not great there. All right, sketch the graph of this, labeling the asymptote with its equations and axes, intercepts with their coordinates, state the range. Lots going on. So we're going to consider the transformations from that. So if I've got y equals f of x equals 2 to the x, what would I do to make this, let's put a y equals there to make it an equation. What I would do is y equals negative f of x take 2 plus 2. That's what I would do to f of x to make this function here. Okay, so again, reading by the function technique is important. So I can see here that this is going to be a reflection in x axis. It's going to be a translation to right, and it's going to be a translation to up. Okay, so let's take care of the 2 up first. That's going to take the normal asymptote of y equals 0 and send that 2 units up as well. So our asymptote is going to be along there. All right, what else? Well, 2 to the x has a y-intercept of 0, 1. let's take care of these things here. Reflection in the x-axis changes the y value. That's going to be -1. Translation 2 to the right means that's 2, -1. Translation 2 up means it's 2, 1. So the y-intercept moves to 2, 1, which is there. What is the y-intercept? Well, that occurs when x is equal to 0. Is it +2? Yeah. Y equals -2 to the -2 plus 2. Y equals -1/4. So it's 1/2 to the 2, which is 1/4, plus 8 on 4 equals 7 on 4 equals 1 3/4. So here's 1, there's 1 3/4 right there. And what about our x-intercept? That occurs when y is equal to 0. All right, so what we've got is the same base, so we can equate the powers. 1 equals x take 2, x is equal to 3. Ready to sketch. Not bad. 0,7 on 4. Label the asymptote with its equation. Whoopsie. Axes, intercepts as coordinates. Check. State the range. Y is an element, so moving up from -infinity up to the asymptote, but you can't touch the asymptote, girls. Okay, got 3 to the x, and this is what we want to sketch. So let's just write the function. So we'll go y equals 2 times 3 to the x take 1 plus 1. Let's also see if we can state these transformations. So it is a dilation 2 from x. It's a translation to, not 2, 1, right? And it's a translation 1 up. All right, so what I do is I always take care of the 1 up first by noting that our original asymptote, which would have been at y equals 0, is now at y equals 1. Then I do the y-intercept. So 0, 1 was the original y-intercept of 3 to the x. Dilation 2 from x changes y, 0, 2. 1 right is going to be 1, 2, 1 up is going to be 1, 3. There it is there. Now let's just double check that. So what I'm going to do is slam 1 into this and make sure that 3 pops out as a result. So 1 goes in, 1 take away 1 is 0, 3 to the 0 is 1, 2 times 1 is 2, 2 plus 1 is 3. Winner, winner, winner. Okay, that's fantastic. All right, now let's get an x-intercept, a y-intercept. So we're going to go y equals, y-intercept occurs when x is equal to 0, 2 times 3 to the -1 plus 1. Y equals 2 lots of 1/3 plus 1. Y equals 2/3 plus 3/3 equals 5/3. And sometimes I find that hard to plot 5/3, so 1 2/3. There's 1, there's 2, that's roughly 1 2/3. So 0, 5 on 3. And there's no x-intercept, okay? So we're not going to get one. So we can simply rule out or draw our function going through there. All right. What function is produced when this undergoes the following transformations? Let's map this thing. Dilated by a factor of 5 from x changes the y. Dilated by a factor of 2 from the y-axis changes x, 2x, 5y. reflected in the y-axis changes x. Translated 5 units in the positive direction of x. And I'm just going to roll this one into the same one. 5y, positive and negative direction. So that's take 3. X dash, y dash. X dash is negative 2x plus 5. Y dash is equal to 5y take 3. What we're trying to do is sub for y and x, so I need to make y and x the subject. So x dash take 5 all over negative 2 equals x, and y equals y dash plus 3 all over 5. So my exponential function, which started as y equals 3 to the x, will become y dash plus 3 on 5 equals 3 to the, and I've got x take 5 all over negative 2. Right, now let's tidy up after ourselves. So what we're going to do is say that I'm going to drop the dashes in the next part of this. So y plus 3 equals 5 times 3, 5 take x all on 2. Y equals 5 times 3, 5 take x on 2, take 3. All right, so there it is by mapping. Now by equation. I find this harder, and I would go with the by equation technique in the exam, but let's just see what happens here. Dilated by a factor of 5 from the x-axis. So we're starting with f of x. 5 from the x-axis is 5 f of x. 2 from the y-axis is 5 f of x on 2. Reflected in the y-axis, 5 f of negative x on 2. Translated 5 units in the positive direction of the x-axis, 5 f of negative x, positive x take 5, all on 2. 5 f of negative x take 5, all on 2, plus 3. All right, so there's our by equation there. So what I need to do is slam that into f of x and recall that f of x equals 5 to the x. No, 3 to the x, I think it was. 3 to the x. So let's do this thing to make my new function. So y equals, so we're going to do 5 out the front of 3 to the, and x is negative x take 5 on 2 plus 3, and that's fine. Okay, what I did with this one here is pass the negative through and flip those around. So y equals 5 times 3 to the 5 take x on 2 plus 3. So you can see there we yielded the same result, I think at roughly the same speed. I think there's more scope for error in this method personally, but it's not for me to decide, you decide. All right, so the second part of this will be looking at this exponential function f of x equals e to the x. So e to the x is not like another version of y equals a to the x. E is a very, very, very specific number, okay? And in mathematics, it's an irrational number that is 2.71828, just like pi, and just like the Pythagorean constant. So pi is 3.14. Root 2 is 1.4 something or other. This one here is another mathematical constant. It's called Euler's number, and make sure you pronounce Euler's name correctly. So Euler, not Euler. Okay, so yeah, he's a mathematical genius, this bloke, and you can do him the service and the credit and give him the credit he deserves by making sure that you pronounce his name correctly. In class, I would go on to state how the number is derived, and it's based on growth. Okay, so The way we get it, and the way I would teach it in class, is to explore this concept of a bank and a bank offering interest. Okay, and what happens here is that instead of the bank paying interest, which is 100% every 365 days or every 1 year, what they do is they start to compound it more often. Okay, so what they do is they give out 50% interest twice a year. And note that that's a better deal. So instead of getting $2 at the end of the year, you're going to get $2.25. And what if they do it more often? They do it every quarter year. Okay, so they pay out a quarter interest 4 times a year. What we're going to get is $2.44. It's even better. What if I do it 100 times a year, 1,000 times a year? Okay, let's have a look at what happens here. Let's try it out on the calculator. So we've got 1 plus 1 on 100 to the power of 100, and we get that there, or we get 2.70. What about if I do it 1,000 times? 2.71. What if I do it always? Okay, so if this is not always, but I've got 1, 2, 3, 4, 5, 6. I've got 3, 4, 5, 6. Oops. Now they match. What I've got here is if I do it 1,000,000 times, is that 1,000,000 or that's 100,000? So if I do it 100,000 times, I get that. Now let's just try something here. I'm going to hit Shift and 4. Okay, and I'm going to do e to the power of 1. All right, I want to go into decimal mode because I want to get it to approximate what e to the power of 1 is. And you can see here that actually this is the way the formula or e is worked out. It's by using this. And what we let happen is n, or this value here, the 1,000, approaches infinity. So we make that indefinitely large. And what we say here is that you can think of your money as being compounded continuously, always, indefinitely, infinitely, okay? And we say that this is a natural number because continuous compounding is natural. It doesn't depend on any particular unit of time. Now I implore you, go check this dude out. Okay, so his name's James Grime, and he does just the greatest explanation of E you can possibly imagine. He uses a very similar approach to this one, which I think I pulled out of Cambridge. Okay, so just look him up, James. This is the search to do, James Grime E number file with PH. Right, it is absolutely worth your time because it's important that we're going to use E a lot, and I want you to know how and why it exists and why it's kind of an important thing. Okay, so we'll finish off this lesson with just a quick sketch of a function. This is an exponential function, but what we're going to use instead of using a base 2, base 5, base whatever, we're going to use a base E. And remember, every time you see E, make sure that you replace it with 2.718 ... That's what you're thinking of. Don't think of that as a variable like f of x equals a to the x, where a is a value. Like, this is a number. It's 2.7, okay? It's not a variable, so it's very important. All right, now what we're going to do for this is think about what the y-intercept is, first of all. Basically, we're going to do the transformations, okay? So we're going to have an asymptote at y equals 2, so let's do that first of all. So here it is, y equals 2. And what we're going to get is the x-intercept. So x-intercept occurs when y is equal to 0. So we're going to get a y-intercept, which occurs when x equals 0. So f of 0 equals e to the 1 plus 2. Okay, now how would I plot that point on the number line? Well, again, what you've got to do is go 2.7 roughly plus 2 is equal to 4.7. So here's 2, here's 4, here's 6. 4.7 would be roughly here. All right, how am I going to label the point? Am I going to put 0 and 4.7? Hell no, I'm not. All right, so what I'm going to do is put in what number that represents, which is E plus 2. Okay, and let's just try it. Here it is here. E plus 2 is 4.7. Okay, but we've got to put our exact value in. Okay, there's no need for values either side of that to give it shape. We know that this is a standard exponential function. The y-intercept is that. Let's just send it through, making sure that it looks exponential and it's got asymptotic behavior. See that, like that veering away from the asymptote there, again, not good. All right, so that's all I wanted to do is one graph there. Go practice these questions here, but remember, E is a base, 2.7 dot, 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 dot. It's a number, just like if I go, oh, sketch a function base 2, then you'd be like, oh yeah, base 2, yeah, that's fine. If I go base E, and you go, oh, what is base E? Like, oh, couldn't it be anything? How am I supposed to sketch that? No, the base is 2.7. Have I laboured that point enough? Hopefully I have, girls, okay? So 5A, 5B, let's get ready for the next class after this where we start solving.